Okay, today I'll start with PLC scan cycle. So basically in a cycle, the PLC completes executing an instruction in 3 steps. So in the first step, it checks all the input bits actually, or the status of each of the input ports, and it stores that data into its memory to be used in the next step. And the next step is to execute the program or execute a particular instruction. So after executing the instructions in terms of the inputs which were stored in the first step, the necessary output results are generated and they are stored in the memory to be further processed in the next step. So in the third step, the results which were generated in step 2 are updated towards the output ports. And this is a cyclic process. These 3 steps repeats continuously in each cycle of the operation. Now, regarding the programming languages for PLC, the common type of programming languages which are used for different manufacturers are the ladder logic diagram, the functional block diagram, sequential function chart, and Boolean mnemonics. So we are going to mainly focus on the ladder logic programming because the PLC that we have in our lab, it is compatible with ladder logic programming. And in terms of ladder diagrams, the program has to be made. And for the other types, functional block diagram, it's like a drawing block, the whole operation in terms of block diagrams, um, more like some of the Simulink models that you build. So drag and drop type of thing actually in terms of different multiple blocks. The sequential function chart is similar to making a flow chart. So you are familiar with flow chart, how to make flow charts. So uh, maybe in order to represent an algorithm, flow chart is normally used. So sequential function chart is similar to that process actually. In terms of a sequential chart, the set of instructions are drawn, and in case of Boolean mnemonics, it is a bit similar to assembly language where different operations are having a specific symbols or abbreviations. Using those abbreviations, a code can be written. So these are some of the common programming methods used by different manufacturers. Now, to discuss about the ladder diagrams, first of all, we can have a look at a simple electrical circuit and how that circuit can be represented in terms of a ladder diagram. So maybe you are familiar with ladder diagrams. Maybe in your machine course you had studied to represent some complex electrical circuit in ladder diagram form. Okay, but here let us I mean have a quick overview of how a circuit can be redrawn in ladder diagram. So this is a basic circuit or representation or conventional circuit representation, and it is this the figure on the right hand side. It is just the analog or I mean equivalent ladder diagram representation. So for example, if a DC source is connected between these two terminals, L1 and L2, as mentioned over here, there is a switch and a motor, a simple series connection between them, shown over here. In case of ladder diagram, the power rails or the terminals where the power has to be given, those are represented by vertical lines as shown over here. And in between those vertical lines, as denoted over here as L1 and L2, similarly, which is denoted over here, In between these two power rails, the rest of the circuit components has to be placed. So here we only have a switch in series with a motor. So a switch and a motor can be connected in series in between these two power rails. So basically the name ladder diagram representation comes from the fact that the two vertical lines, the power rails, normally are similar to the vertical sides of a ladder, and the horizontal lines where the circuit components are placed, those are somewhat representative of the different rungs of a ladder. So this sort of a representation have a shape of a ladder. That's why the name is suggested as ladder diagram representation. Now, if there were other loads connected in parallel as well, suppose a lamp could be there. So if multiple loads are there, suppose this lamp can be here represented like this in parallel with the motor. If there are multiple branches, suppose another resistor, let's say, which is driving another motor 2, suppose. So if there are multiple branches, then that can be also represented in between the vertical lines, such as this that I am drawing over here. So the whole circuit representation can be converted into analog as ladder diagram representation. So similar representation is actually used while developing the set of instructions in case of PLC.
Sir,
So
sir,
yes,
sir, if we have more than one input sources, so in that case, how many vertical lines will be there?
the vertical lines will always be two. I mean, they, because in case of PLC, if we consider about PLC, multiple different sources can be there. I mean, the input devices that you are using, they are, I mean, may have a different voltage level. The output devices that you are using, they can have a different voltage level. But basically, using the ladder diagram, we are representing, I mean, in case of PLC, we are representing what? How the CPU should execute different instructions. And if you remember from previous class, both the input modules and output modules were separated from the CPU. Do you remember why?
Yes, sir.
What was the reason?
So to electrically isolate the circuits so that the input or output cannot damage our CPU.
Okay, and at the same time, your input and output voltage levels might be very high compared to the operating voltage of the my CPU, right? So maybe the CPU needs only 5 volts signal to operate. So for the CPU, this is the only voltage source that will be available. So there is no possibility of multiple sources available to the CPU. Okay, so for that reason, we don't have to bother about the portion that whether multiple input devices are operated at different voltage levels, or uh, I mean uh, different output devices are operated at different uh, output voltage levels or not, because the CPU is always going to be operating in 5 volts, because the CPU is isolated from the input side and also from the output side using opto optocouplers. So a common 5 volt source can be considered for the CPU. And if you ask in general about if there is different voltage source, then uh, I mean, in general, if there are different voltage sources, then a single ladder diagram would not be sufficient to represent that particular. Uh, uh, I mean, electrical circuit into a ladder diagram form, because a single common voltage source is necessary in order to uh, I mean draw the two vertical lines and all the elements that is shared by that particular source.
So if we can find the Thevenin equivalent circuit, then can it be done?
If you find the Thevenin equivalent circuit, then you are actually replacing all the components into a single resistance. If it is only consisting of a resistive element, you are converting all those into a single resistance and maybe a single voltage source. So in that case, you can draw the ladder diagram, but it will be only two vertical lines, an equivalent Thevenin resistance, and the load that you are going to connect to that particular network. Now, this ladder diagram programming method is mostly common to all the different manufacturers. Now, like the previous diagram, which was shown to represent a particular circuit, uh, the same technique can be used to represent the different set of instructions in case of uh, writing a program into the PLC. So here as well, the uh, two vertical lines represent the power rails, and in between them, the input devices and output devices, the relation between them are established in equivalent circuit diagram form, and there could be multiple different lines of instructions, and the instructions are executed from the first line, from left to the right, and from top to bottom. In this sequence, the instructions are executed, and the execution process takes on the three steps that was discussed earlier. This is the step 1, step 2, step 3, which is storing the inputs, then executing the program in terms of the stored inputs, and then the outputs which are stored in the second step. Based on that, updating the signals at the output ports. Now, after drawing some set of instructions, while finishing the program, the user should enter this particular block, end or return, so that the CPU can understand that it has to start from the beginning again, and this process will go on. So continuously the inputs will be checked and the outputs will be updated accordingly, and unless the user interrupts the power supply or intentionally stops the process, this process of scanning will go on. Now the things that I tried to discuss there, in a sense, described over here as well. So let me go through them quickly. So each rung on the ladder defines one operation or one instruction in the control process. Now the ladder diagram is executed from left to right and from top to bottom. And when the PLC detects the line where end or return these things, either of these things is mentioned, then it goes back to the beginning again. So while drawing the instructions in the ladder diagram, it has to be kept in mind that each rung should contain at least one input and one output. So a particular line cannot have only a single input without any output, or any single output without any input device. Now, the representation of the input and outputs are done in analogous electrical form. So Normally, in order to represent the input devices, as mentioned in the previous classes, contacts are used to represent the input devices or status of the input devices. So if it is necessary to use normally open contacts, then this sort of a symbol is used. If it is necessary to use a normally closed contact, then this sort of a symbol is used. And in order to represent an output device, this sort of a symbol is used, which is represented as the output coil. So the symbols are kept analogous to the symbols normally used for relays. And a particular device, which means a particular contact or I mean the address of a particular input port might be repeated, because if it is necessary that a particular input device is going to operate multiple outputs, in those cases the notation of a particular device can be repeated multiple times. And the inputs and outputs, they are actually identified in terms of their addresses. So the ports at which a particular input or output device is connected, depending upon the address of that port, the input and output devices are designated while drawing the diagram. And normally the notation of the addresses are different for different manufacturers. Now, to discuss a little bit more about the ladder diagrams, we can talk about the different logic functions, how to implement the logic functions, whether AND or not, or NAND, nor these logic functions, how they can be implemented. So here on the right hand side, the hardware connection, how the hardware connection can be done, that is shown, which is obviously you have seen in the previous class as well. So if we want to implement an AND logic between two inputs, so at two different input ports, two different switches A and B can be connected. And on the output side, any output device can be connected. Maybe it could be an LED or a lamp in this case. So how these input switches A and B should be related in order to generate output according to this truth table has to be informed to the CPU in terms of the ladder diagram. And the ladder diagram used for this implementation of AND gate is shown over here. So as it is necessary to implement an AND gate, what we can do, we can use two normally open contacts and place them in series with the output coil. So here actually this input A, while drawing the diagram using a software to write the code into the CPU, the corresponding address of the ports has to be mentioned. Now here it is shown as input A, input B, or as output, but in actual case, the address of the ports has to be written. So the first normally open contact that is being used, its corresponding address has to be P00 according to this hardware diagram. The second input port is P01. So the normally open contact associated with that particular switch has to be represented by P01. And the output coil has to be represented by the address P40 according to this particular diagram. Now for the AND gate, when both the inputs are high, the output is supposed to be high as well. So when both these switches, these push button switches are pressed, both of them are going to send a high signal. And when both of them are getting a high signal, what is going to happen? The CPU is going to, according to this diagram, it is going to close the normally open contacts, and when both the contacts are closed, this output coil is also going to get a high signal as well, because the path for current flow is complete in this case. Now, although I have represented in terms of an ladder diagram using contacts and coils, but can anyone suggest what is actually happening in the CPU when this sort of a diagram is, let's say, is I mean, given as an instruction to the CPU?
So it deals with different clock pulses.
Can you repeat or elaborate a
It
little bit more?
it, it operates different clock pulses, I think, for different inputs.
No, actually, the CPU is actually has a common clock pulse, right? Based on which it operates. The thing that it does, it changes the state of these corresponding memory locations. So if it is getting a signal from this input device, suppose A, what it is going to do, let's say when we are using a normally open contact initially, the CPU is assigning a 0 at this particular memory location, P00. But whenever this particular port is getting a signal, in the diagram we are mentioning that it is getting closed, but actually the CPU toggles the bit from 0 to 1, the memory bit at this particular memory location. Similarly for the other addresses as well, the CPU is actually changing the state of those memory locations to either 0 or 1. But in terms of this diagram, I mean pictorial representation, I can say that we are representing those status of different uh, memory locations in terms of contacts and coils. So if you see a contact that is normally open, you can say that it is representing a binary bit 0, and if you see an closed contact, it is quite, in a sense, representing a bit of 1. Now, similarly for the output as well, if the output is getting any complete path, then it can be said that the bit at the output should be having a transition from 0 to 1. Now, if all logic has to be implemented, then according to the hardware diagram, you can see that there is no necessity of changing any connection to the external devices. The switches and the output device can be kept as they were connected before. But in order to change from AND logic to OR logic, the only change has to be done in the software in I mean in form of the change in the ladder diagram. So both diagrams A and B are representative of the OR logic. Any one of the two formats can be used. They are just basically indicating that the input contacts associated with both the inputs should be connected in parallel. Then when either of the inputs are providing any signal to their respective ports, those corresponding contacts are going to be having a transition, or it can be said that those corresponding addresses will have a transition from 0 to 1. And if there is transition according to diagram, it can be said that, let's say, if this contact is getting a transition, it is becoming closed, then the path for the output will be completed and the output coil will have a signal. So it will be a high signal in this case. So in this way, so different combinations can be checked as well. So if any one of the two inputs are giving a high signal, the output is supposed to be high, and the corresponding memory bits will also have a transition from their previous status. Now, for example, without changing this hardware connection, keeping the hardware connection intact, if we want to use only this particular switch A, in order to implement a NOT gate or inverter, then uh, what could be the possible ladder diagram? We are not bothering about B. Let's say we are only going to consider about input A. Using this switch, we want to implement a NOT gate. Then how we can establish the relation between this particular input and the output?
Or
Sir,
using closed switch.
Yeah, so between the vertical lines, if we use a closed switch and connect the output along with it in series, so the address of the closed switch will be P00 and the address of the output coil will be P40. If the diagram is drawn in this pattern, then it would be sufficient, because normally the contact is kept closed, so your output is getting a high signal, but whenever this switch is pressed, this particular port is getting some high signal, and if it is getting some high signal, it will have a transition from its initial state. So the contact was represented to be normally closed initially, it would be open then, and the path for the output coil will also be open, and there will be a transition in the output as well. So that is shown over here, that you can use a normally closed contact in series with the output coil. Now, even if the switch B is connected, you are not removing it from the external connection. Still, your operation will go on smoothly, because you in the set of instructions you are never introducing the address of this particular port. So even if that is connected, that is not going to hamper the operation of the CPU. So similarly, the NAND gates and the NOR gates, those can be also implemented, and keeping the same hardware connection. So in the instruction, now in case of implementing NAND gate, instead of using normally open contacts, normally closed contacts can be used, and they can be put into parallel. So that would be sufficient to implement the NAND gates. And in order to implement NOR gates, normally closed contacts can be used, and they can be collected in series along with the output coil, which would actually give you the required output. Now here, in order to draw these diagrams, let's say, I mean, in case of NAND gate, what you can say that A prime, B prime is actually going to give you the desired output if you want to rewrite it in terms of Boolean expression. So A prime, you can say that it is a normally closed contact. B prime, it is a normally closed contact as well. And they are having what should I say? I mean, AND logic in this case. So okay, so I have done some mistake. So it should be like this: AB whole prime. So that's where the problem was. So according to De Morgan's law, it should be represented like this. So now it's more logical, because you are having to normally closed contacts, and if they are related by a summation, which means OR logic, then you can put these two normally closed contacts in parallel and connect them with the output coil, and that is supposed to be representing your NAND gate. Similarly, for NOR gate and also for XOR gate, the relationships can be formed. Now for XOR gate, we can write as A plus AB prime plus A prime B. So this A and the complement of B is having an AND logic. So a normally open contact and a normally closed contact can be placed in series with each other. And on the other hand, they are having an OR relation with A prime into B in A prime into B. So the complement of A can be represented by a normally closed contact and in series with a normally open contact associated with B, and these two branches can be connected in parallel in order to form the XOR logic. Now let us finish our today's discussion with an example of a motor starting and stopping circuit, a simple circuit where at the input side we can have two switches, one to start the process of start the motor running, and another switch to stop the motor. And at the output side at port P40 we have a motor connected. So I think now you can suggest that what should be the ladder diagram for implementing this particular operation. So anyone suggest, suppose these are the two vertical lines, how we should take the contacts and how we should connect them with the output coil.
So can we take a NOT gate, sir?
NOT gate? I mean, how? I mean, how you want to implement the NOT gate?
Sir, when it's normally closed, sir, then it will give the signal start, and when it's otherwise, then it stops, sir. So I guess that's
Okay, that is, suppose you are saying in terms of NOT gate, but let's say you have to implement this, that you are having two switches. Using one switch, you have to start the process. Using another switch, you have to stop the process. So how would you have to give the set of instructions, including these two input devices?
I guess one open switch and one closed switch in parallel.
In parallel, suppose like this is the open switch. What would be the corresponding address?
P00.
P00. And okay, then if we connect another contact in parallel and then connect them with the output coil, then would it serve your purpose? I mean, okay, you are pressing the start button. This contact is supposed to be getting closed. Now, when you are going to press the stop button, will it stop the flow of, I mean, let's say flow of current towards the output coil?
So I didn't think this is true. I just remembered a similar logic in from our machine course. I thought that would be it.
Okay, no problem. I mean, you say that whether it would serve your purpose or how you should then connect it, this contact, this normally closed contact.
So we have to press the start button once, then the path will be closed and the power will flow, and then there will be another switch to disrupt that path.
Yes, so how would you disrupt that path? Because
So
if you are
directly,
connected in parallel, it will not disrupt the path because the alternate path will always be there.
sir,
Oh,
by
sorry, in
connecting the
series, in
process
series.
using parallel with the coil, sir.
Yes.
Sure.
By
That is
connecting the
that works too, sir.
So we have to disrupt this path between the start button and the output coil. So the normally open contact, normally closed contact associated with P01 should be placed in series so that this I mean input port P01, when it is receiving any signal, this normally closed contact becomes open and this path is no more giving a complete connection to the output coil between the two power rails. Okay, now a little bit earlier, one of the students was saying that a parallel connection with the input contact should be there as well, according to a concept that you studied in your machine course. Are you still there?
Yes, sir.
Well, your idea is actually correct because there is going to be a parallel path necessary. Okay. Now, before that, let me say that the switches that are normally used along the input ports, those are normally push button switches and they are momentary switches. What is the operation of a or difference between a momentary switch and a static switch?
when pressed a momentary switch, it will again after we remove our pressure, it will be again closed.
Yeah, so when you are pressing the momentary switch, as long as you are pressing, the switch will be closed. When you release, the switch will become open again, right?
Yes, sir.
So the momentary switches that are being used at the input side. So for example, for this motor, if you want to keep it running, if you are using momentary switch, you cannot press it forever, right? You need to do some changes so that when you release the switch, the motor still gets the necessary signal. So a parallel path or bypassing path should be created, like one of the students said a little bit earlier. So this purpose of this parallel path is to, eliminate that particular problem, that when you are releasing the switch, this P00 is returning to its initial state, which is normally open, but you want to ensure another path that will keep the motor getting the necessary high signal. Now, what should be the address of this particular contact? Now, each contact that you insert into a ladder logic diagram, they should be associated with the memory address. So what should be the memory address associated with this particular contact?
According to the diagram, it's confusing. So
Okay, so if you recall the concept of relay, let's say this output coil is, let's say it is the electromagnetic coil of a relay. Then if I say that this is the corresponding normally open contact with this particular relay, obviously these are not physical relays, just the concept of relay. So if this coil is getting energized, then what is supposed to happen with this particular normally open contact? So
it will close.
it will close. So once this start switch is pressed, this particular memory location P00 is going to get high momentarily. This contact is going to get closed. The path is complete, so the motor will start getting a high signal. This coil is going to get a high signal, and whenever this coil gets a high signal, its corresponding contact should also change its status, so it will become from normally open to normally closed. And now if this starting switch is released by the operator, the contact corresponding to the P00 pin will again become normally open. However, as the output coil was already energized, its corresponding contact will remain closed, and this should give a continuous path, and the motor will continue getting a high signal until this stop button is pressed. So when this stop button is pressed, the contact associated with P01 will have a transition, and it will open the path, and the output coil will stop receiving the high signal. So this is actually an important thing to remember, creating this sort of bypassing paths, because in most of the cases the inputs which are momentary switches or which are sensors, because sensors are, maybe they are going to get a signal for small amount of time. So once the sensor gets the signal, the sensor needs to actuate some process, and it needs to keep that process running until another instruction is given or some manual instruction is given. So using this sort of a bypassing path, which is coupled with the address of the output coil, is often necessary while implementing different applications. So this concept is important to remember. Now this is often also called, this sort of connection is called latching connection. So the output condition of the output is latched along with the input. Now, whatever I have discussed, those things are also summarized over here. So, for example, this is the initial stage when only the connections are made, but no signals are provided either from the starting button or the stopping button. So this would be the initial status of each of the components. So along with P00, the corresponding contact will remain open. P40, its contact will also remain open. P01, as a normally closed contact is taken, it is indicating that this path is closed, which is indicated by this blue rectangle over here. Now when the starting button is pressed or actuated, this path is closed now. So this port P00 is going to receive some signal. So as this port is receiving some signal, its corresponding contact will get closed now. As this contact is getting closed, this path is now complete. As this path is complete, the output coil will also receive a high signal. And in terms of relay concept, we can say that the output coil has got energized and its corresponding contact is getting closed as indicated over here. However, in terms of microprocessor, they are actually these operations are not in terms of physical relay, but they are in terms of changing the state of memory bits. So the motor will start running, and now even if this push button is released, as this contact connected in parallel has already been closed due to the high signal at the output coil, the output coil is going to receive continuous high signal until the stopping button is pressed. So when the stop button is pressed or the stop button is actuated, as this port is P01 is going to receive a signal, it will have a transition from the normally closed contact to normally open. So you can see that the blue rectangle which was indicating the closed states, so that is removed now. So as it is removed, it is disrupting the continuous path towards the output coil, and the output coil will be de-energized, or the bit will have a transition from 1 to 0. So the motor will again stop running. So when the stop button is released again, then the whole thing would be in a sense reset, and upon pressing the start button again, the motor can be running again. Now apart from this, let's say along with port P41, let's say I'm connecting a lamp L1. I want this lamp to glow as long as the motor hasn't started running. Suppose this is a red LED, and along with port P42 we can connect a green LED. So the red LED will glow when motor is off, and the green one will glow when motor is on. So what could be the possible set of instructions can be drawn over here in this ladder diagram to implement these two operations as well. Now we have increased our number of output devices. Our input devices are still those two switches, that is starting button and the stopping button. Along with the motor, we have added two other output devices, one red LED and one green LED. The red LED will emit light when the motor is off, and the green LED will emit light when the motor is on or the motor is running. So how we can implement this operation, these two additional operations in this ladder diagram?
So by implementing not operation for between the motor and the radiality, and implementing or operation and operation between the motor and the green LED.
Okay, okay, let us focus with the first one. So first of all, you said a not operation with
With the
motor and
and the radiality.
radiality, right? So, okay, let me start from here, okay? So you are saying a not operation, so I am taking a normally closed contact, right? So what should be the address of this contact?
So P41.
P41. Okay, let's set P41 as you have said. And
It will
on
be
the
00041. So
output side, what should be the address of the coil?
so same, sir. P00041.
Okay, I'm writing P41. Now, when is going to P41 is going to get energized?
So when the motor is off, sir.
When the motor is off, okay, but then when the motor is on, it is supposed to, when the motor is on, the red LED is supposed to stop and the green LED is supposed to start glowing, right? So how would you stop the red LED and start the green LED?
So the same way, you implemented the P0040 along with the P0000 by giving a alternative path for the current flow. I think, I'm not sure.
Okay, whatever you have said, I mean, what will happen if I change the address like this?
Yes, sir. Yes, sir. When P40 will be on, then P41 will be off.
But until P40 is on, P41 is supposed to get a high signal, right?
Yes, sir.
So this is sufficient for the first one, that turning on the red LED until the motor, or for the duration the motor is off. Now when the motor is on, as long as the motor is on, you want to indicate that operation by turning on the green LED. So how you can implement that?
By simply adding a series with simply adding the green LED in series with the motor.
Okay, no, not in series. You can, if you have multiple outputs, you have to connect them in parallel. Okay, so suppose for the same input configuration, if you want to connect multiple output devices on the output side, okay, for this particular line, says for the 0th line over here, for this input configuration, if you want to have multiple output devices at the output side, they should be connected in parallel, not in series. That is the general convention. And as you want to drive two different, high signal to two different output ports, you have to define it using their corresponding address. Okay, so this could be one possible representation to operate these two output LEDs. Now, the thing that I have discussed, the same thing is implemented over here. So but you can see the addressing is done in a different way, because this is taken from the book, and the book is in the book it was done in terms of the addressing used by another manufacturer, but the concept is quite the same. So this portion is same as starting or stopping the motor. Now additionally, if there is a lamp to indicate that there is no power applied to the motor, which is same as we were discussing about the red LED. So normally close contact can be taken. Whenever the motor coil is getting energized, its corresponding contact will have a transition from open to close to open, and this corresponding lamp will stop glowing. Now another lamp which is going to glow after the motor is getting powered. So a normally open contact can be used to power this particular lamp. But instead of using this another line of instruction, this particular output coil could have been connected over here as well, like it was done in the previous slide, and the address of the coil should be Y432. So whenever the motor is getting output power, this lamp would also get output power, and whenever the motor is getting output power, this particular contact will open and this lamp will stop glowing. So both are actually correct, implementing in this way or this way, but only one has to be followed for a particular implementation. So up to this I wanted to discuss in today's class. Now if you have any question you can ask, otherwise we can conclude today's session because the Maghrib prayer time is also near.
So no questions.
Mm.